Hello, this is my IBM data science capstone. My project is predicting the stability of the electrical grid. The data set was an open source data set from the UCI machine learning repository. The data points include the following: power consumed, produced from each house and the supply station itself, P1, P2, P3, and P4. Response time of each house and supply station, tau 1, tau 2, tau 3, tau 4, and the price elasticity for each building and supply station, G1, G2, G3, G4. There was also another column for stability, which was taken from a characteristic equation, and the positive and the real root was used for this. And if it was positive, then the electricity generation was considered to be stable, and if it was unstable, the value would be negative. And then finally, there was a categorical column showing whether if it was stable, it would have a value of 1, and if it was unstable, it would have a value of 0. The data quality assessment, there's really not much to say. It was it was a very clean data set with no missing values. Um, Use case, this project will be using binary classification to predict whether the grid is stable or not. It's useful as a way of determining whether the power supply meets the power demand, and I believe would be useful for independent system operators or electrical engineers overseeing operation of the electrical grid. So the solution for this particular problem will first be using a machine learning method, a gradient boosted tree model, and then we would also be comparing it to a deep learning method, which in this case is a pytorch neural network. With this, we'll predict whether the electric grid is stable based on the power consumed, produced, the response time, and price elasticity. We'll use a Jupyter notebook to show the exploratory data analysis, model pipeline, and neural network solution. And the results were accuracy of the gradient boosted tree was 95.4%, and the accuracy of the PyTorch network on the test set was 92.1%. Technology choices. Project was done on IBM Watson Studio. The data was in a CSV format and then uploaded into the Jupyter Notebook as a Pandas data frame. Pandas was used for the exploratory data analysis. Spark 2.1 was used for the gradient boosted tree pipeline, and PyTorch was used for the neural network for binary classification. Model 1, the Spark pipeline, was composed of two parts, the vector assembler, which took in all of my input features, which in this case were everything besides the stability numbers, besides the stability characteristic column and the categorical column. It was then set equal to features. The second part was the classifier, which was the gradient boosted tree. The features column, in this case, is the features output from the vector assembler, and then the label column was named stability F. The stages were then assembled in a linear fashion, so vector assembler was put first, followed by the classifier, and then the data was fed through. There's a sample output on the screen, and bin eval was used to evaluate the accuracy with the accuracy metric, and the accuracy acquired again was 95.4%. We got good results from the GBT, but it was important to see how it would compare to a deep learning solution. So I used PyTorch because it was easy to make the neural network and test it. So I used that. The data was split into 80% train and 20% test using scikit-learn's test train split function. The network architecture had to be slightly complicated to be able to accurately classify from all the input features. There was a bunch of them. The neural network architecture, the details are in the notebook, but basic outline is there was one input layer, 3 hidden layers, and 1 output layer. The loss function used was BCE loss, binary cross entropy loss. The atom optimizer was chosen with a learning rate of 0.01. I tried to use stochastic gradient descent just to test out different optimizers, but SGD didn't work out as well as Atom. I'm guessing because you need to be very careful with your hyperparameters. If you don't choose them right the first time, it'll not get as good of a result. So the model was trained for 500 epochs. There's an output on the screen here. And the accuracy of the network was then determined with a function, and the accuracy again was 92.8%. And there is my GitHub repository for the project. So if anyone's interested, please feel free to check it out. Thank you very much.